My pleasure to share with you today Engineered Wood A to Z, Opportunities and Challenges for Engineered Wood Construction. Before we get started on the content, I would like to begin with a brief introduction of APA for those of you who may not be familiar with our association. You may think of us as the American Plywood Association. However, today we are APA, the Engineered Wood Association, in that our members are manufacturers of not just plywood, but all the glued wood products that you specify on your projects today, manufactured not just in the United States, but also Canada. Our members produce wood structural panels, plywood and OSB, as well as I-joists, glue laminated beams, glulams, SEL members, including PSL, LSL, OSL, many of the products that we are going to discuss today. As a nonprofit trade association, we have three main divisions: quality, technical, and field services. Our quality services division is required by the building codes that these materials are tested by a third party, and our auditors will visit the mills, inspect the manufacturing process to make sure that they are meeting the standards, and the end result is in the grade stamp that is printed on the product. So we will look at some grade stamps today, as this is a benefit to you to be aware of how to specify the materials and then later be able to check that grade mark to make sure that it has what you had intended printed on there and meets your requirements. Our technical services division is located in Tacoma, Washington, and there we have a laboratory with engineers and wood scientists conducting research and projects to further construction using engineered wood. Many of the code changes that are put into the NDS or Chapter 23 of the Building Code come out of our research and our technical services division. And finally, we have our field services division, where I'm the local field rep in the Southwest. I'm located in San Diego, California, but also cover California, Arizona, Nevada. On our website, you can find the closest engineered wood specialist to your location, and we work together as a team to assist the end users of these products. So we work with builders, building officials, contractors, engineers, architects. So if you have a question about any of these materials today, of course, during the webinar, next week, next month, or next year, please do not hesitate to contact us. It's our job to be a resource to you, and also to provide the feedback from you to our members, again, to further their development and how they implement the issues into construction moving forward. A brief note on a few APA recognitions. I wanted to just quickly mention that for those of you who regularly specify glulam beams, you may have noticed that AITC is no longer in business, and APA has acquired, and we are now maintaining their ANSI standards. So moving forward, it's the same number designation, yet instead you'll simply note ANSI A190.1, and these are available on our website for free download. Our agenda today will begin with a discussion of the top 10 framing errors, which also gives us an opportunity to look at the advantages to using these materials and how to best utilize them. And then we will also touch on advanced framing techniques and finish with a discussion on all wood podium construction. On the note of our documents, I have included many references to our publications on our website so that you can later download those for future reference. Beginning with the top 10 framing mistakes, and we reorganized this program to not just look at the mistakes, but what did they have in common, and what were the 5 main ideas that if you were aware of them, you could prevent these mistakes occurring on your project. So rather than just going through issues, we have reorganized this to look at the common threads. So the first, wood has a strength direction, is really the most important one we're going to discuss today. And then we'll look at wood moves, consistency counts, moisture intrusion, and load path continuity are key. If you think of any piece of wood in its simplest form, you can compare it to a bundle of straws. And you take a bundle of straws and you push it or pull it apart and you'll find that it's very strong parallel to grain. You take that same bundle of straws and you apply a load perpendicular to grain and it's easily crushed. So you'll want to avoid that perpendicular to grain loading, or at least be aware that it's not the strongest way to load it. And so these products are manufactured with this in mind. We'll begin with our wood structural panels, and we're going to go through these just like the load transfers through a building, starting with our panels to our joists to our beams. So with a plywood panel, you'll notice in this simple drawing that the panel is manufactured by taking a series of plies of wood, laying them up in a strategic fashion, and then gluing them together with moisture-resistant adhesive. So the face and the back have the strong direction of the wood and the long direction of the panel. So you can remind yourself that long equals strong. Secondly, the veneers adjacent to the face and the back are going to be oriented in the opposite direction. By doing so, you're going to be increasing the stiffness of the panel and the dimensional stability. As that panel gets wet, or as wood gets wet, it wants to expand, and dries, contract. So by cross-orienting those veneers next to one another, you're going to therefore increase that dimensional stability. And finally, by using the moisture-resistant glue, that's key to holding it all together and keeping the moisture out. Oriented strand board is manufactured with the same properties in mind. So if you look closely next time you see an OSB panel, you'll notice that the majority of the strands at the face and the back are oriented with their strong direction of the wood and the long direction of the panel. And then the strands in between are oriented in the short direction, again maximizing your stiffness, your dimensional stability, and the same glue is used to tie it all together. So rather than specifying plywood or OSB, we recommend specifying rated sheathing with the proper span rating, thickness, durability that you need, rather than one product or the other, as they are manufactured with the same attributes in mind. Using the generic specification will open up that spec for the widest availability in construction. I mentioned the span rating, and both of these products have a uniform span rating that's applied for the span rating printed on the grade mark. So for our roof span, you see first that the deflection is limited to L over 240, the live load is 30 pounds per square foot, and the dead load is 10 pounds per square foot. For our floor, L over 360 for the deflection, 100 pounds per square foot for the live load, and 10 pounds per square foot for the dead. What is the most common live load that you see for your floor spans? Yes, it can be 100, but more often you're looking at 40 or 50 pounds per square foot. So this is helpful information to be aware of as well, that the span rating that's stamped on the product is based on 100 pounds per square foot live load, which is likely greater than what is needed for your design, most applications. The first framing mistake that I'd like to share with you is installing these panels incorrectly. So as you note on the right-hand side, we have our diagrams showing that the panel needs to be installed in a continuous application, so across at least three supports or two spans as shown here. On our left-hand side, of course, that would be a simply supported installation. And the span rating, in addition to the loading criteria that I showed you in the last slide, is also based on a continuous span loading. So if you have a simply supported span, you're going to be exceeding the design criteria. There are instances, as I mentioned as well, long equals strong is the majority. There are some cases where the strength is oriented in the short direction of the panel, and it will have an arrow designating it in this fashion. Cases where you may see this would be some wall panels that are made specifically for a wall installation. I'll have it labeled with the strength axis in the short direction. Or possibly if you're doing a panelized roof construction where it's a very large roof, they're laying those panels up in the parallel application, as shown here, where you would have your subpurlins running the length as opposed to perpendicular. And that is done for a specific application. The engineer should be aware of that. So again, you want to, likely they often just still go with this type of panel, but recognize that the span rating that's stamped on the panel is not for that application. So again, coming back to our first framing mistake, you see that if the panels are oriented parallel to the supports as opposed to perpendicular and across multiple supports, it's not going to be meeting our requirements for installation. Some supplemental information: if you find that perhaps the roof panel was installed parallel to the supports, it was intended to be perpendicular, now what is your allowable live load, for example? So here we have an example for a 3216 panel, the span rating, and you see for a maximum span of 24 inches on center, you would only have 15 pounds per square foot allowable live load, as opposed to the 30 pounds per square foot allowable live load for a intended panel at 32 inches on center. So the span rating shows you your allowable spacing of your supports. What do you suppose is incorrect in this picture? I'll give you a second to digest that. There are a couple things. First, long equals strong. So again, if you look at the panels, you'll notice the grain of the wood is going in the long direction, indicating the strength axis. And that's the way you'd want to see these panels installed, as done for the majority of them, with the exception of this panel on our left. The other issue is the panels are very narrow. Are they too narrow? What is the minimum width the panel needs to be to meet the requirements? So most panels are 4 feet wide by 8 to 10 feet in length. So when your panels are narrower than 4 feet, we have some recommendations that you can use, and you might want to include in your structural notes to cover this instance, because we do design in 2D and build in 3D, and this will likely occur during the construction, and so by providing the notes ahead of time can provide the builder with guidance. So for APA publication R275, if you at least have 2 feet or a 2-foot wide panel, you're fine. You don't need to do anything to reinforce it. If it's between 16 and 24 inches, then you would need to provide 2 roof clips at the lower edge or block the lower edge. So if this panel happened to be 18 inches wide, for example, then you would need to have 2 of these roof clips between each of the spans. Between 16 and 12 inches, then you would want to provide blocking at your lower edge. And if it's narrower than 12 inches, you need to block your upper and your lower edge. Next, we're looking at our roof panel installation, and this diagram is provided in our Engineered Wood Construction Guide E30, as well as that table that we looked at a few slides back. So as I mentioned, I'm providing you with tools to go back to later. We also have builder's tips that cover many of these same instances, and the nice thing about the builder's tips is that they're 1 or 2-page documents that quickly go through these common framing mistakes. They provide a simple picture as shown here and steps to prevent buckled roof sheathing, for example, from occurring. And a new feature that's available on our website as well is our mobile tips for our builders tips. So again, that's something else you might want to utilize, take with you. Many people on the job sites have their smartphones or tablets that they're using as well today. On the left-hand side, you'll see a typical grade mark, which again I wanted to quickly go through for you so that everyone's on the same page on how to read these. The E30 also begins with a section on grade marks, and it has a whole variety of what they may look like, as you can see some differences in this line, for example. This is the grade of the panel. it says rated sheathing in this instance. It could say rated siding, rated ply form, so that just indicates the use that the panel was manufactured with to be used for. So rated sheathing can be used as your floors, roofs, and wall panels. The next item down is the span rating, 3216. As I mentioned before, this indicates the allowable spacing of your roof and your floor supports. The first number is the roof spacing. So in this case, that would allow the trusses to be spaced at 32 inches on center and still meet that 30 pounds per square foot live load design criteria that we looked at before. That also assumes that the panels are installed with the strong direction across our supports and across at least 3 supports or in a continuous application. The second number is the allowable spacing of your floor supports, and knowing what the design criteria is of 30 versus 100 pounds per square foot, it makes sense that you're going to notice the first number for the roof is always larger than the second. Below that we have size for spacing. This is an option that you can specify in your specs, and what that means is that the panels have been manufactured to allow spacing to occur at the job site. We recommend an 1/8-inch space around the panels during installation to allow for the panels to acclimate, as we will get to in our next bullet point of framing mistakes and how to prevent them, the big ideas. Below that is exposure 1. That is the durability of the panel for rated sheathing. That's going to be covered by your tiles. The walls are covered by your siding or your stucco. Your floors are covered by hardwood or carpet, for example. Exposure 1 is all that's needed. The other option would be the panel might say exterior. That would be useful for a engineered wood siding panel that's going to be exposed for the life of the structure. So in that case, you would want it to say exterior. In all other cases where it is going to be covered by some other material, exposure 1 is sufficient. The next line down is the thickness of the panel, and this changed a few years ago now, but you'll notice that the fraction thickness is down here, 15/32 category, and then the thickness is stated up here as a decimal thickness. You are going to continue to specify the fraction, and just be aware that it has moved in its location on the grade mark, but that is still what you'll use for your specification. If you're trying to identify where the panel came from, the member mill number is stamped on the grade mark in this location between this bar, and as we see here, it's a number that you can go onto our website, type in the number, and then the contact information will come up. You can also contact me or your local engineer wood specialist with that information as well. And then finally, we have the manufacturing standard shown here. So PS2 is a U.S. product standard, as well as PS1. PS1 is only for use for plywood. It's a prescriptive standard for plywood. You're looking at those larger veneers of wood where they can visually inspect the number of knots and knot holes, for example, assigned in the letter grade. So PS2 is more of a performance standard where the panels are manufactured to the member's liking and the mill's liking, and then they test it to show that it meets the structural properties that are required. So PS2 and PRP 108, that's the APA performance rated panel standard, are very similar in that nature. The next diagram here on our right, or figure, is for wall sheathing. And yes, long equals strong is still true, yet what is the main purpose for our wall sheathing? Shear resistance. And for the shear capacity of the panel, that doesn't matter if the panel is installed parallel or perpendicular to the supports, as the shear capacity is based on the thickness and the grade of the panel, as well as the size and the spacing of the fasteners that are attaching the panels to the supporting members. If you're running the panels horizontally across your studs, then you would need to provide blocking along this edge for the shear capacity, of course. As I mentioned before, we have the panels that are typically 4 feet wide by 8 to 10 feet in length. And often our plate heights are 8 to 10 feet in height. So being able to install the panels vertically is often more cost effective for the builder as opposed to going horizontally. And then the trademark is shown here on the left-hand side. As we discussed a moment ago, this span rating is for floors and roofs. It's not for the wall per se. There could be a wall grade mark, and then that would have just the wall 16 or 24OC stamped on there for a wall application. For our floors, again, we are back to long equals strong. You want to have the long direction across your supports, across at least 3 supports. And then you'll notice here on the grade mark underneath, rather than rated sheathing, this says rated sturdy floor because it also has a tongue and groove edge. So this tongue and groove is shown here. It provides edge support along the long length of the panel. If you did not have a tongue and groove panel that you're using for your floor sheathing, you would need to provide blocking underneath that long edge to support the floor sheathing. As I mentioned, our engineered wood construction guide is our E30, and I've included some tables in here for your reference just to demonstrate what you might use this for, how it can reinforce your design and specifications. So quickly showing you for this particular table, and this is for your roof load application, a 32/16 span rating. And you'll note if your supports are 32 inches on center, your trusses, then you have 30 pounds per square foot live load. Yet we often have them at 24 inches on center, so you would actually have 65 pounds per square foot live load. So again, this should make sense to us as engineers that as the supports come closer together, your allowable live load goes up. And this can be a resource to you if you're looking at an existing panel and wondering, what your allowable live load is if the supports are closer. This is also useful to keep in mind. Even without your plans on hand, if you walk into a job site and you look up at your roof panel, it says 32/16, your trusses are at 24 inches on center, you know very quickly that it meets the span rating condition. You walk into the next job site and look up at your trusses, they're 48 inches on center, the span rating is 32/16. Now you know that you need to take a second look. Moving from our panels to our I-joists, and we're still on the concept of wood strength direction. The loads are transferring from the panels to our repetitive framing member, which in the engineered wood world would be our I-joist, which is created with 2 flanges, typically of lumber or laminated veneer lumber, LVL, with a web section that used to be plywoods, more commonly OSB today, and then glued together with the same moisture-resistant adhesive that's used for the panels. These are an efficient use of the wood fiber in that we're eliminating that unnecessary material through the web section, creating a lighter member to work with, built-in handle for ease of construction. And just comparing an I-joist to a sawn joist, you can see the savings in the wood fiber when they're both spaced at 16 inches on center. Yet, as these materials have been selected to maximize their strength, you can generally space them further apart, so you're seeing even a greater savings of 46% of the wood fiber when you space your I-joist at 19.2 as opposed to 16. The flanges are carrying your bending loads in an idealized manner, and then the web section is going to be transferring your shear load. So what happens to these products at a job site? You might have some hole cutting occurring, and each of the manufacturers have their unique hole cutting tables that can be used to identify if the hole that was cut meets their allowances. Yet you can also use your engineering knowledge to think about the load distribution and how these forces are being transferred to identify the safest place to have your holes cut. And so with a simply supported, uniformly loaded I-joist, we know that we're going to have zero shear at the midpoint, and then the shear accumulates out to either support. You can take or visualize a triangular shape from the bottom of the flange at the support to the bottom of the top flange at the midpoint, and this shape identifies your allowable hole size at any place along the span. So as we see on left and right, the sizes, but you'll notice on the left-hand side, we're showing the allowable size, yet on the right, you'll notice that it's always best to put the hole away from your flanges. So some rules of thumb with hole cutting is that you want to stay at least 1/8 of an inch minimum away from either flange with your hole, regardless of what the allowable hole size is at any point. Spacing holes, you need to space them 2 times the diameter of the larger hole, unless you have several small holes that if you circumscribe them into a single hole that met the allowable hole size, you would not need to space them 2 times apart. If you have a non-circular hole, again, depending on how they're cutting the hole or what the tool is that they're using, they may not have a circular hole, and of course at these locations you have stress concentration, so therefore you're limited to 75% of your maximum round hole diameter. Knockouts are commonly provided by the manufacturers, so you'll notice that it's a perforation or a perforated circle along the length. They're not knocked out initially, but it's encouraged to use these whenever possible as opposed to doing field cutting. Putting it all together, what do we see that's incorrect in this picture? A couple things. Even without being able to see the midpoint or the whole span length, if you started to use that trick of running a triangular shape from the top of your bottom flange at the support out to the bottom of the top flange out at the midspan, you would see that we quickly exceed your allowable hole size by these large holes that were cut. And secondly, the spacing of the holes does not appear to meet your 2 times diameter of the larger hole. And what's wrong here? We never want to cut the flanges. So when you have a hole that you believe exceeds the allowable hole size, you have several options to consider. You may want to sister in a new joist as though that joist wasn't there. You could frame around it, block around it, support that section to transfer the load around. You can contact the manufacturer who can provide you with an engineered solution. Moving from our I-joist to our structural composite lumber, this is a new designation of grouping together these engineered wood beams that have some similarities. As you note here, the wood grain of the veneers or strands are primarily oriented in the same direction. So when we looked at the panels, we noted that they cross-oriented the veneers and strands for plywood and OSB. With these materials, the strands or the veneers are running in the same direction for every single ply in order to maximize that bending capacity. And other items of note, they're sawn to consistent sizes. The strength properties are published on a proprietary basis by the manufacturers, and then they're recognized by the evaluation report. So that can make it challenging as a designer to know how to specify and when these different materials. So the SCL members include laminated veneer lumber, LVL, and LVL is created by taking, again, these veneers of wood, laying them up in the same direction, very similar to plywood. And again, how plywood cross-oriented, this is taking the plies and laying them up all parallel to the length. And then a photo on the right-hand side showing this. LVLs are available in low, medium, and high strengths. So again, if you're looking at which class to specify, you'll just want to think about what the load need is if you're going to be using this as a header versus a girder, for example. And then the other SCL products, we have parallel strand lumber, PSL, which again, this is created very similar to OSB in that we're using strands, long veneers that are clipped into strands, but they are laid up parallel to one another. Another key item to note here, strand length to thickness ratio is around 300. And PSLs are very strong engineered wood beams. So this is something you're going to want to use for your largest loaded materials. The next item would be laminated strand lumber, LSL, and you'll note here that that ratio went from 300 now to 150. And then lower on the scale is OSL, oriented strand lumber, and then the ratio has gone down to 75. So as I mentioned a moment ago, for LVL, they have a low, medium, and high strength classes provided all in the one product. With the other SCL members, you would likely use your OSL for your low class, LSL for your mid-class requirements for strength, and then PSL for the high strength. As far as framing mistakes when it comes to the SCL products, here we have hole cutting again. Can you go out to the mid-span and cut out the majority of that middle section where we know shear is 0? Well, no, because we know that we have a much larger load that's being carried by our beams as opposed to our joists. So there is the availability for hole cutting, but it's not as flexible, if you will, as the joists because it is carrying larger load. And we have a document here, Form G535, Field Notching and Drilling of LVL, which shows us our allowable hole sizes. And I know that you can't read these figures. I just want to show them to you so that you know how to reference this in the future. Generally, you're looking at a up to 2-inch hole for a maximum hole size, and that depends on the size of the LVL. And then if you look closely, there's this hatching area, and this is very similar to what we discussed with an I-joist, as we note that it's in the middle third and the middle third of the depth. So the depth and the span. Just like as we looked at with our I-joist, we know we have minimal shear there. That's the ideal place to cut holes. This other figure gives you a lot more flexibility. If your beam is at least 7¼ inches deep or deeper, you can have up to a 1-inch or smaller diameter hole basically anywhere along the span and in the middle third. All right. Another document for field notching and drilling would be for Glulam. So we're coming to Glulams next. Similar intention as far as our structural composite lumber. The Glulams are used for our beams. They're available in a medium and a high strength class, similar to the different SCL products. And so where you can cut those holes, again, is the same concept of you want to go where there is minimal shear. There is the ability to cut holes when you get to your supports, but now we know that shear is critical the closer you get to your supports. And we also want to avoid that perpendicular to grain and the tension zone in particular. So if you need to cut a hole towards your supporting area, you want to go in the top quarter of the beam as shown here. And so the hatching is shown to indicate where your allowable hole sizes are. For both the SCL as well as the Glulam, you're going to have the same spacing of 2 times the diameter, the larger hole. And for the allowable hole size for a Glulam, there's a couple of rules of thumb to keep in mind. Either a single lamination, which is often 1.5 inches depending on the species of the wood that's used to manufacture the Glulam, or 1/10 of the beam depth. So again, for field notching, that's very limited. That doesn't mean that you can't design a larger hole size, as we'll see later on in the presentation when we look at our wood podium case study, the engineer actually allowed holes up to 5 inches in size, but he designed them for that case. This is when the framer or the electrician just has to cut a hole for their access, and they're not consulting with you up front to make sure that where it's happened is okay. So you have a lot less flexibility because it's being done without your structural review. How about a hole vertically through the beam? And this is true for both Glulams and our LVL document. The same calculation is shown. So for a vertical hole cut, you would take a strength reduction of 1.5 times the hole diameter divided by the beam width. And again, the forms are referenced here for your use down the road. And in the example of a 6-inch wide beam with a 1-inch diameter, that would actually end up being a 25% reduction. And where do we see vertical holes being cut? In these nice great rooms where we're using a Glulam beam to admire the natural beauty of the wood. You may also have a ceiling fan mounted cut vertical hole through that. So the good news is often when we're using these beams for an aesthetic application, they're often sized for appearance, oversized for the structural requirements, but you should still be aware that that reduction would need to be applied. A Glulam, just in general, as we see in this slide, is created by taking the wood laminations, and they're laid up in a horizontal fashion. And so we're getting that uniformity of the load in the same direction. And because they are laid up top to bottom, there are a few different unique characteristics that you can take advantage with Glulam, as we'll see. The typical widths are 2.5 to 10 3/4, and the laminations, as I mentioned before, are 1 inch 3/8 for southern pine or 1.5 inches for Doug fir. With the Glulam, like all of the engineered wood products, but it's most visible with Glulams, you can see here the elevation of a Glulam beam where they were able to manipulate the wane section where the bark of the tree had been, or the knots and knot holes are distributed. You minimize, this will again enhance the appearance as well as the strength by minimizing these naturally occurring strength characteristics, strength weakening characteristics, as well as a finger joint. If you look closely, this is where the wood was spliced together. This would also cause a weak point in the member, so being able to manipulate where those occur can enhance the strength and beauty. With a Glulam, as I mentioned before, with the horizontal layup, they can do a balanced layup where it's the same strength of wood top and bottom, which makes this most versatile for any application, whether it's a continuous application or a cantilevered beam. Whereas if you are going to be using it and it's simply supported and you know you're going to have your maximum tension on the bottom, compression on the top, you can do an unbalanced beam layup where the best wood is placed in the bottom, the next best in the top zone, and then something less in between. And this simply reduces the cost of the product, but it becomes very important that it's installed in the correct manner. Another design feature for Glulams is the ability to use camber. And so camber, as shown here, is simply the curvature of the beam that is put in there during manufacturing. And it can be specified either by inches or a radius of curvature. For stock beams, it's important to note that there's very little to no camber provided in those. And this is also shown in a table in our Engineered Wood Construction Guide E30. For example, stock beams are typically 3,500 to a 5,000 foot radius, and on a 20-foot beam, that's a curvature of 1/8 of an inch or less. So when would we want to use camber? If deflection is controlling the design, for example, you can use the camber there to make the beam work in a case where it wouldn't otherwise. On your very flat cases, stock beams, you don't have to worry about camber being a concern either. So when you have a cambered beam or an unbalanced layup, you want to make sure you're installing them in the correct fashion. and the beams are labeled top to designate, of course, the top of the beam. In this case, this would be representing turn over please. So when you have the glulam installed upside down, we know that in an unbalanced layup, you just put the strength in the wrong location. For camber, now it's curving the wrong way, so it certainly needs to be reinstalled the proper direction. If you have this happen to you on one of your projects, we do have testing that's been done, and there used to be a much more severe reduction that was required. So there is, depending on the beam and the loading, it may be more like a 25 to 30% reduction as opposed to a 50% reduction in the past. So seek out those tables if you need it. The other thing you may not be aware of is that glulams are available in I-joist compatible depths as well today, and this is helpful just for minimizing the space of that floor section. And I said earlier that glulams are available in a medium and a high strength class application. So our traditional glulam would be our 24F bending capability. Well, there's also the high strength glulam beams that are manufactured in different fashions. A common way that is being done is using LVL for the top and bottom laminations, and the LVL allows us to eliminate those finger joints that we looked at earlier. So bringing up the stress class now to 30F 2.1E. Another glulam to be aware of, and we did not get into the fact of architectural appearance. There's different, for glulams, framing, architectural, industrial. What you want to be aware of is that there are glulams on the market, though, that are available in an architectural appearance with a full framing width and I-joist compatible depths. And the idea here is just to maximize your versatility and ease of construction. So that concludes the first big idea. And as you know, we have a lot of other things I'd like to cover as well today, but that is really the most important one to prevent framing mistakes from occurring, as well as a good overview of how these products are maximized in their strength and application. So what happens when wood gets wet? It expands. And when it dries, it contracts. And so you want to keep that in mind as far as what is the moisture content of the product during or immediately following manufacture versus installation versus in service. So we recommend, as I said earlier with the panels, an 1/8 of an inch space around your edges for every panel that's installed, whether that's for your roofs, your floors, or your walls. And it's for that initial acclimation. The panels are very dry, 2 to 6% moisture content. During the pressing process of the mill, they're going to travel to your job site, and depending on where you're building and at what time of the year, that moisture content is going to fluctuate greatly, and it's going to expand generally. So the 1/8 inch space is there just for that initial acclimation. You're going to enclose it, and you shouldn't need to have that space for the life of the structure necessarily. It's just for that initial installation. And so as I mentioned, you want to have it around all edges. In this roof diagram, you see that we have roof clips, and the roof clips often have an 1/8 inch spacer provided in them as well. So that's a benefit of using roof clips along this long edge, but they still need to space the short edge as well. Often they'll use a nail there just as a spacer. If we don't properly space the panels, you may have this situation, which is our buckled roof sheathing. Structurally, this isn't compromising the panel. It's an aesthetic concern, but certainly they're not going to be happy about it, and so you want to prevent this from happening whenever possible. So again, that 1/8 inch space at your edges, long and short. Of course, you can't just look at this and say, well, that's it, and make that jump to that conclusion. You're also going to want to check the span rating, the thickness of the panel, make sure it's oriented the right direction, that there's ventilation in the roof or the attic space. So all of these items do need to be reviewed, and as I mentioned, our builder's tip, How to Prevent Buckled Roof Sheathing, which is available as a 2-page PDF, or as well as our mobile tip, goes through all those quickly as well. For our wall sheathing, the same is true with the 1/8" spacing. And we do have a tech note. This goes over some high-risk applications where you might run into more of a risk for wall buckling. And this photo shows it in practice. And you'll notice on the right-hand side you have some very tight nailing, as is more common on the West Coast, where we have earthquakes, so shear walls are nailed in a more tight fashion. And they did space the panel, which is great, but you notice that on the left-hand side, using the straight edge, that the panel did buckle. So the panel is going to find the path of least resistance. If the panel is nailed so tightly that it can't grow or move into that space, then it might buckle in between the studs. And so when you have tight nailing or vertical installation parallel to the supports, which we often have those together in a shear wall application, then we recommend tacking it into place first, allowing the panel to acclimate, and then filling in the shear nailing. And so I do see that being done in many instances, but not in all cases. So something, again, you might want to add to your structural notes or at least be aware of. Again, structurally speaking, it's not a problem, but for aesthetics, it certainly is and will have to be fixed. So as a structural engineer, some other things you might want to consider too, if you're trying to decide between panel thickness and nail spacing, is going to a thicker panel to be able to go with lighter nailing, which will help the panel stay flat. The thicker the panel, that's a benefit to prevent buckling, as well as the lighter nailing as well for resisting that movement to occur. On the concept of wood moves as well, that would apply to beams, not just to panels, and so we have a lot of connection philosophies. And what's good in both of these pictures is we're showing that you're using a bucket to support that member. However, on the right-hand side, the connections at the top will prevent that beam from bearing into the seat, and instead it will be resisted up here, the potential for splitting to occur. Similar concept is shown here. I took this amateur photograph myself, and you'll notice that there is a space where the beam should be resting, and it was resisted here by the bolts, and so we have splitting that occurred in the beam. So it's something that you want to think about in your design process is to provide the support and bearing whenever possible, to allow some movement if you need to have these bolts, or having the bolts down here closer to the bottom where it is in support. Consistency counts. We don't recommend mixing engineered wood and sawn lumber in your floor, for example. You have different stiffnesses and deflections, often different sizes, so that load path isn't going to be shared equally. Even structurally speaking, they're both fine. The floor may feel different from one portion to the other, so rather than mixing and matching, we recommend you are consistent, either all sawn joists or all I-joists for that floor. On the topic of overdriven fasteners, this is a common question. The good news is I think it's less commonly happening in the field. When I'm out at job sites, I always look for this out of curiosity to see how often I see it, and I'm not seeing it as much anymore. I think that this is due to the improvements of the nail gun technology. We don't have as many nails being overdriven as they were in the past. But if it does happen to you, here on the left-hand side you see a case where the nail was overdriven, and essentially now you're looking at, instead of a 1, 2, 3, 4, 5/8 panel, a 1/2" panel. So you've reduced that shear capacity as a result. On the right-hand side would be your properly driven nail. And we do have a white paper, TT012, to give you guidance on how to address this. And so if less than 20% are overdriven by less than an eighth of an inch, you don't need to worry about it. If you have more than 20%, less than an eighth, or any greater than an eighth, you can add one additional fastener for every 2 that are overdriven. Unless, of course, you're already really tightly nailed. Can we add additional fasteners then? No, because if we do, we could possibly split the supporting members. So in that case, you would want to perhaps take a second look at your design, and as we saw in that previous photo, maybe with the reduced section that's now being held together in the panel, would that work for your needed shear capacity, for example? If not, the other solution may be to use staples, and you can't add just enough staples to work in conjunction with the nails. You would have to staple it as though the nails weren't there. Another alternative, or a case, is what if it's not actually overdriven? What if the panel has swollen around the nails? Is there a reduction? And the answer is no, because again, if you went back to this picture, there should be a third picture here that would show you would basically have what's seen on this right-hand side, but then the panel would have swollen around it. And so again, it's still holding the same size of members for the wood in place, so you would still have your original design values. And as long as the panels are allowed to dry before being enclosed, the panels will regain their strength. And so how you can tell if this is actually due to swelling as opposed to overdriving is you know the history of the project. Has there been a lot of rain? Do you see other indications of exposure like a graying to the panel or some streaking in the nails on the panel? So using all of that information, you can come to your conclusion. For tight nailing, the footnotes to the shear and diaphragm table talk about staggering the nails. So the question is which diagram shows the staggered nailing that they're intending in the tables? And it's actually the right-hand side. The left-hand side, this is staggered, but it's staggered from one row to the other. The intention for the table is to stagger the nails within the row itself. And the reason why is to prevent splitting. So here we show that when we have in a single line or lined up along that same grain of wood, you're actually creating a wedge that can pry the wood apart because, again, wood is weaker perpendicular to grain. So as shown here, simply taking the nail and spacing it very small amount apart by staggering it is going to prevent that splitting from occurring. And another photo showing from our lab, and of course we don't think that you're going to be using a Sharpie or your framers will be to lay out the staggering. But the good news is human nature, I think we have a lot of built-in staggering happening, and for our tight nailing, the code does require special inspection, so this should be checked in that framing check. Along the idea of consistency is that in addition to mixing I-joists with sawn joists would be to just having inconsistent joist spacing. So again, this is creating the same concept of where the floor is going to feel different here as opposed to in this location. And lots of different floor framing feels shown in this floor layout. A lot more fun to design, of course, but what we'd recommend would be to be consistent whenever possible. Minimize the spacings and the spans to get the same feel throughout. Number 8, the number one complaint with floor sheathing is squeaky floors. So how do we prevent squeaky floors? We recommend using a glued and nailed floor system. So the glue is there to eliminate the squeaks. The nails are there for the structural attachment. In this picture, you're looking up at the floor sheathing. You have the I-joist below it, and what do we see? You could argue that they were consistent, but they consistently missed the flange. And so as you walk along this panel, the panel lifts up, and the nail's going to squeak or rub against the flange, and so there will be noise there. And so perhaps we should eliminate the nails and just use the glue to provide that connection. Yet, you look over here, and this is a business card, which means that there's certainly no glue in this location. So how would you check the glue? The glue also has many different recommendations depending on the manufacturer as far as temperature and how you're going to lay the glue. So again, long story short, APA recommends the glue there to tie it all together to prevent that squeaking sound, yet the nails staples, screws, whatever is used to attach the panel to the supporting members are there for the structural connection. How many of you think the common nail is the common fastener at a job site today? So again, with nail guns, we have many different sizes, but you'll notice that APA, we continue to list common nails in our recommendations, and that's just for ease of specification, understanding that you are likely going to find an alternate that's being used instead. So rather than just saying 8-penny common, at a minimum, you also want to provide the diameter and the length of the nail too, so that when they do provide you with an alternate, it's quick and easy for you to show that it meets your design. And so a code report you may want to use would be ESR 1539, and that's produced by ISANTA, the International Staple and Nail Tool Association. And it has two parts to the report. The first part is a substitution table. So again, it gives you some prescriptive alternatives. For example, an 8-penny common at 6 and 12 is equivalent to 8-penny coolers at 4 and 12. The other option is it gives you the design values for these alternate fasteners up front. So if you know what the framer is going to use, you can start there rather than having them provide you with the alternate. Moisture intrusion, item 4. And we have our Build a Better Home section on our website, a series of documents that talk about how to keep moisture out of a structure. And it's applicable not just to residential, but also commercial construction. And you can summarize it as the 4 Ds of wall design. You want to deflect as much moisture as possible from the building to begin with, and then provide that drainage plane for moisture that might get behind that exterior, that first line of defense. Drying capability for the moisture that once it gets in, you have to provide a path for it to get back out, and then of course using durable building materials to begin with. What do you suppose is poor about this picture? We are beginning with just deflection rather than, we use our gravity generally to deflect moisture away. They are deflecting it right into a window where the windows and doorways, any penetrations into your walls and your roof needs a lot of extra attention to detail to make sure that we are properly flashing and detailing to keep moisture out. So this is terrible to have the moisture source pointing right at this prone location. If the window were not there, second, you would still, rather than having the water running down the side of the house, you would prefer that there was a gutter to carry it away. Within the building as well, you want to think about moisture path, and many of building materials have the ability to wick moisture through them. Cementitious materials as well as wood both have this ability, so an air gap is there as one way to prevent the moisture from transferring from one material to the other, as opposed to on our left-hand side, we see that we just provided a moisture path from the two products. Another issue with moisture, and we talked about this earlier with panels, if it's an exterior rated panel, that means it's fine for use outdoors for the life of the material. How about beams? And one option, as shown here, is to, with your Glulam beams, you can either do a preservative-treated Glulam or you can do naturally durable species. And so your natural durable species options would be Alaskan yellow cedar, Port Orford cedar. There are a few others, but these are most common on the West Coast. And what you'll want to be aware of is they do have a slightly lower stress class than 24F. 20F, I think, is typical. So again, be aware of that. Yet in an exterior application, they're often sized for appearance as opposed to the structure as well. Preservative treated, on the other hand, they can preservatively treat southern pine without incising it, so that's a great option if you want to just go with your traditional stress classes that you're used to, and to do so without the appearance of having it preservatively treated. And so even on the West Coast, where we generally have more Doug fir, there are preservative treated southern pine beams available for this use. And another photo demonstrating a combination of the two because the roof is providing protection for a large portion of this truss. They chose for the top chord and the web sections to use normal Doug fir, untreated, and then for the bottom chord was created with Alaskan yellow cedar. And our final idea to keep in mind is load path continuity, and our last web seminar focused on that, on the lateral load path in particular. But here we see a case where just in our vertical load path, you want to make sure that we are continuing the forces and supporting them from origin all the way through the foundation. Excessive notching, those field notching and cutting of glulams and LVLs also talks about what is allowed as far as notches go, and generally speaking, it's again 1/10 of the beam depth. So here we see we've clearly exceeded that. And supporting our members, many pre-manufactured hangers are available, and it's great. Take advantage of them whenever possible, but make sure you have the right hanger for that material. So here we see that this hanger wasn't meant for this I-joist size. Multiply members. This may be a preferred alternative. It looks like 3 LVLs that were laid up as opposed to a single member that same size. Perhaps this is easier for construction that can lift these smaller members up, but what's important, of course, is that it is connected. In particular, in this case where we see it side-loaded in one direction, parallel-loaded on the other, if this isn't connected, which we can't see any connections in this picture, then we know that it's not truly acting as a hybrid member. For our hold-downs, we see a couple of framing errors here. You have concrete spalling where the strap was not enclosed properly. And then another potential issue here is where the hold-down has been bent. And what do you imagine happened here? Likely missed the anchor bolt location. They had to epoxy it into place, which at a minimum we see that is an extra cost. It's a delay in time. Special inspection is required. So for all those things in consideration, you want to get it right the first time. And so these are our 5 ways to prevent them. I have a couple more topics that I want to share with you. First, advanced framing. What is advanced framing? There are a lot of different names for it, and it's been around for several years. Inline framing, stacked framing, optimum value engineering, OVE, and what APA recognized recently was that there is a renewed interest in it for a variety of reasons, energy savings, cost savings, the sustainable nature of being more efficient in our wood use. So for all of these reasons, we researched all of the different details and sources that were out there on this topic and gathered the best details that we felt were applicable to modern construction today and packaged these into our Advanced Framing Construction Guide, APA Form M400. So you can find it on our website. We also have the Advanced Framing CAD details available for free download on our APA CAD website as well. And it's a suite of framing techniques. It's not a take-all-or-leave-all concept. And so when I speak with people about advanced framing, that's one of the negatives I hear, is that there's one aspect of advanced framing that they don't like. And if there's something you don't like about it, you certainly don't have to apply it. You want to apply what works for you, and that may vary from project to project. And when you're learning it, you don't want to try to implement it all at once anyways. You want to slowly implement it so that it's done correctly. And as you see the benefits, you can take on more. So the more you do, of course, the more your savings will be. And so what it may utilize, again, these are some examples shown in this picture, but rather than 2x4 studs at 16 inches on center, we're looking at 2x6 studs at 24 inches on center. So these deeper studs spaced further apart are going to provide more area for insulating within the wall cavity, which again one of the key reasons that people use advanced framing is to maximize the energy efficiency of the building. So as we go towards more efficient structures and perhaps even zero net energy buildings, being able to bring down the demand load is very useful even before you start adding renewable energy resources on the structure like photovoltaic panels. Other concepts shown here is to size your header properly. So in this case, you see in the picture that the floor is framing into this wall. It's only parallel loading over here, so very little load is really going into this header. So let's size it for the load that it's seeing. On the other direction, even where they are taking on a larger load, is taking a second look at your header tables. When I was doing design, we often had our header span tables that we would create and use for the majority of our projects, and on a 2x4 wall or a 2x6 wall, you would fill the cavity up with a header of that same width. So the concept here would be, rather than using a full width header, is to use a single ply header or a shallower header so you still have the ability to insulate this header space. The stacked framing is another concept, and this is a more advanced framing technique, and it's not applicable for everyone. In order to go down to a single top plate instead of a double top plate, it requires stacking your framing from your roof all the way down through the wall, the floor, and the wall below. And so the advantage to doing so is, again, eliminating that extra plate, yet on the West Coast, for example, we use our top plates not only to distribute our vertical loads, but also as our drags and our cords to distribute the lateral loads of the system. So again, that's one item that I recommend you really become an expert at everything else first, and if you still want to apply that, you can do so. Why adopt it? As I mentioned, there are several reasons why different designers and project teams choose to implement advanced framing, but the common ones are for energy efficiency, cost effectiveness. As you might imagine, as we become more efficient with our layouts, you're going to be reducing the number of pieces of lumber. The overall volume is likely going to stay the same because we are going with larger members as opposed to the smaller ones, yet having fewer of them will provide you with more opportunity for consistency in that insulation, hopefully fewer cutting and notching mistakes, so that'll all help the cost as well as the waste factor. I understand that that is a huge issue with many projects, is the amount of waste that goes into the dumpsters. So again, being more effective with the material usage up front can reduce the cost. Sustainability, of course, is a goal for many when they're looking at using not only wood, which is a sustainable building material, but using it in an advanced framing method where you're using less of it, so you're being more mindful of the natural resource that you're using. And structural integrity is always key. You never want to sacrifice the structural integrity for any of these details. So if there's a case where you need a larger header, certainly provide the strength necessary. And so again, if you want to insulate it as well as have the load necessary, you might look at an engineered wood header as opposed to a sawn header in order to get that structural requirement met. And one example of this being utilized is shown here, a Sacramento Habitat for Humanity project, which was also net zero energy, 21 points beyond LEED Platinum. They used advanced framing, and the project won a SEOC Excellence in Structural Engineering Award in the Sustainable Design category. How do we use it? So this 4 steps is also provided in the advanced framing construction guide that I mentioned earlier. And so the first step perhaps would be to go simply from 2x4s to 2x6. And you're still going to be spacing them at 16 inches on center. So only one thing has changed. The next step would be to go from 16 to 24 inches on center. keeping your double top plates again to have to avoid the inline framing issue. Step 3 is to incorporate your intersecting wall techniques, energy efficient corners. So rather than 3 stud corners, possibly going to a 2 stud corners, and again looking at your headers of what the load is, how do we maximize the insulatable cavity there as well. And then finally going down to eliminating the double top plates. Superimposing a conventionally framed wall upon an advanced framed wall, you can see the yellow represents your conventional framing where you would have 2x4s at 16 inches on center, possibly an oversized header, a lot more cripples and jacks around your windows and your doorways, your intersecting wall that's not going to be easily insulated, as well as the corner. As opposed to an advanced framed wall where we see again we're using 2x6s at 24 inches on center, possibly a single top plate, a more efficient header size, perhaps a wood structural panel box header for an idea. For your intersecting walls and your corners, one option is to use a ladder blocked wall. So although this doesn't look like a lot of lumber savings, this is really making it easier to insulate that cavity. So on the topic of corners, many people already use the California corner, your insulated 3-stud corner, which, as we see here, allows insulation to be readily installed, as opposed to a traditional corner where you create a hot or cold spot. The other consideration would be a 2-stud corner, and this can be done with either using ladder blocking in the form of lumber or drywall clips. So we have both of these details with the lumber or with the drywall clip provided in our guide. And this can be done as well for our intersecting wall. So again, the idea here is you're bracing the wall, yet making it easier to insulate behind it. With regard to our headers, really taking a closer look at the required load carrying capability at each location, using a single ply header where necessary, and increasing that accordingly to the load required. Another option is to consider a wood structural panel box header, which can be 1 or 2-sided. There are recommendations for spans available in the residential code, the IRC, and we also have a technical paper to provide assistance as well on the engineering application. A couple of things to note if you're using a wood structural panel box header is that you see the strength axis, we talked about earlier, long equals strong, is required to go across the supporting members as opposed to our vertical installation. It also requires a minimum 15-32 thick panel. So maybe thicker than what you're used to specifying. However, if you typically design structures that are already fully sheathed, then this is an opportunity to use that panel that's already there for a header application in addition to acting as your shear capacity or just simply your framing enclosure. Energy Heal trusses is another detail that's shown to really enhance the energy efficiency of the structure. It's also useful as far as your load path goes because you have the ability to lap the sheathing up here to your roof diaphragm above. But with the Energy Heal truss, what you see when you compare it to a traditional truss where the truss would cramp down to this corner is that now the attic insulation is not compressed and it allows you to use a lesser attic insulation. So that's going to decrease the cost of the insulation required for the attic as well as a more efficient system. What are the impacts on our structural installation? So for our sheathing, we talked about this earlier. When you go from 16 to 24 inches on center, we still have the minimum recommendation for 6 and 12 for the nailing at the edges and 12 inches for the field, yet we would recommend a minimum 7/16 thick panel for the 24-inch on center spacing of your studs. If you're using something less than that, that would be a change that would be required. There are panels that are oriented with the strength in the short direction, so that's another thing to consider. As we look at our stucco finish, we have some specific recommendations as well. So you'll notice here, for 24 inches on center, for a vertical installed panel, our minimum goes up from 7/16 actually to 19/32 or 5/8 5-ply or OSB. So that would be what we would recommend for a wood structural panel installed at over 24-inch on center studs with stucco for the finish application. And that's simply to minimize any cracking that could occur in the stucco. If you would rather go with the 7/16, again, long equals strong. So this is one benefit to running the panel and across your studs is you could go with a thinner panel then in this case, yet you would need to block those edges. So there's trade-offs in anything that you've done. The third alternative, as I mentioned, is that there are some panels that are specifically manufactured as wall sheathing, and they have the strength oriented in the short direction, knowing that the builder typically wants to install vertically, so you would then be able to, in this case, use a 7/16 panel that was created with the strength in the short direction of the panel, yet installed vertically. And that's an example shown here, this cross-face panel. I took this photo in the Bay Area last spring in Northern California. And if you zoom in, you would see that this says wall 24OC, and then it also has the arrows pointing in the short direction, and it says strength axis this direction. So summarizing advanced framing, it's really the idea of balancing the cost with the structure and maximizing the energy efficiency of the product. The last topic I wanted to share this morning is our all-wood podiums in mid-rise construction. And this case study was produced by myself and Michelle Cambyron, who is with the American Wood Council. And we wrote this case study for the CEOC convention and compared these two buildings with this new technique. So what it is demonstrating is on our left-hand side we have our traditional podium construction where you have multiple levels of residential, generally out of light frame materials, your wood framing, over a non-residential base or podium. And so this podium level is typically a concrete section, and it's separating a combination of maybe just parking or retail or office from the residential application above. The wood podium is the exact same concept in that you're taking multiple levels of residential construction and you're separating it from the non-residential base but using a wood podium instead of a concrete podium. So the two examples that we compared were Oceano at Warner Center in the LA Basin area, the city of LA, to Galt Place in Northern California near Sacramento. And so the first project, Oceano, as you can see, was a luxury apartments, 244 units, 4 stories above grade, 1 story below, overall height of 55 feet. And it was designed in accordance with the 2008 LA City Building Code, which was based on the 2007 California Building Code, which was based on the 2006 International Building Code. Galt Place, in contrast, was affordable senior housing, 88 units, a total of 3 stories, overall height of 47 feet. And it, too, was based on the 2006 IBC. So both of these projects used a wood podium, yet their function of how the space was used and the size of the building was different. And we thought that was also particularly interesting to share, to compare and contrast for people who are interested in implementing a wood podium into one of their projects. And so architecturally speaking, for this project, Oceana Warner Center, you see that it was type 5A construction, that the first level was S2 enclosed semi-subterranean parking, and then the rest of the structure was R2 for residential, and it used an NFPA 13 sprinkler system throughout. Galt Place was also a type 5A building. The first level, however, was a combination of not just parking, but it was also A2, N, and B. And then the levels 2 and 3 were residential using the same sprinkler system in FPA 13. Structurally speaking, both projects use light frame shear walls at all levels, which is another unique feature of the wood podium, was that the first level was also constructed with wood shear walls as opposed to needing a concrete system at that location. And the wood podium itself for both projects was constructed using wood structural panels with a lightweight gypcrete topping supported by I-joists and deep glue laminated beams. So this photo, or photos, were taken from Oceana Warner Center, and it shows an overview looking down the drive aisle in the garage, and you can see the emphasis on consistency and continuity. So they had their shear walls regularly spaced throughout the depth of the floor system. They used a wider drive aisle to accommodate maneuverability of the cars, and because with the wood shear walls it was a more enclosed parking structure, they wanted to have more light brought in through this wider drive aisle. You notice above, these glue lamps here are designating the hallway above. So they really focused again on stacking as much as possible from top to bottom. As mentioned before, the project used wood structural panels, both projects, and they used OSB and plywood only for the balconies. And then I-joists were used for Galt Place, top to bottom. For Oceana Warner Center, they used I-joists for the podium level, but then sawn lumber for the floors above. The glulams were 2 stress classes at Oceana Warner Center, only a single stress class at Galt Place. So Galt Place being the smaller structure, they were able to utilize 24F 1.8E glulams throughout. Oceana Warner Center, bigger structure, higher loads coming down at that podium level, and the podium itself, because it was just a parking garage, they were more focused on really minimizing the depth of those beams as opposed to Galt Place, where that first level had a mixed use between retail and restaurant, where they were open to having more of an open feel. So for Oceana, they used not only the 24F beams, but they also used the high-strength 30F 2.1E beams. All things considered, you can see the variety of sizes that were required, between 5 1/8 to 12 1/4 inches wide, 10 3/4 to 45 inches deep. So some really deep beams were required. Structurally, steel that was used on the project was used for the columns supporting these very large glulam beams, and they needed to have unique buckets to support these glulams as well. And both teams did price steel beams in comparison to the glulams and found that the steel was more expensive, so they did stick with the wood for that purpose of keeping the cost down. Used the steel for the columns. At Galt Place, they did consider using the wood columns, but again, with the parking, they just felt more comfortable with steel. Design challenges and solutions. The biggest challenge for both of these projects was just meeting the requirements of the code. And so this is more of the architect's responsibility of looking at the heights and areas and the exiting and how that was going to meet the requirements. And so we have already reviewed the construction type and the occupancies that were used, the code sections that they utilized as well. For most of these podium projects, they used the special provision section, which in the 2012 is section 510. I put a line through this because that does not work for a wood podium of light frame wood materials. If you look through the special provisions section, it requires one option would be to have a 3-hour occupancy separation, which you can't do with light frame wood. Another option is to do it with a heavy timber wood podium, which the glulams would qualify as heavy timber, but of course the I-joists and the panels would not. So you could create a wood podium with that section, but not this particular combination that they used in these projects. And so they found by classifying it as a mixed use and occupancy building, they were able to meet the requirements for the fire and life safety and provide only a 1-hour separation between the residential above and the non-residential below the podium. Now the size of Oceana Warner Center needed something more, and so they used firewalls as well. So when you use firewalls, that allows you to break the building into, in theory, individual buildings that as long as each of those buildings alone meet your size requirements, you're good. So they use that to be able to create a much larger overall structure. The question comes up with firewalls and with wood construction, though, is the lateral continuity. So how do you meet the requirements of the firewall, yet at the same time meet the requirements of your lateral load path continuity? And so the Structural Engineers Association of Southern California has a white paper, and their opinion, based on their seismology group, is that the lateral load path trumps the firewall detailing issue, and this actually is available on the ICC LA Basin chapter website that you can look at this opinion statement. And so the detail that was used was, rather than having the diaphragm separate at the firewall location, the wood structural panel diaphragm goes through the firewall. Durability was another concern on the project. How can we take a concrete podium and make it wood and not be worried about the durability? Well, the first thing to be aware of is that these podiums were protected by the building envelope. They weren't getting exposure to the outdoors, so it wasn't a concern as far as that goes. However, how both projects approached it was different, and that's interesting to note as well. So on our left-hand side, we see Oceana Warner Center, where they opted to wrap the entire podium segment, again, with the gyp to get that 1-hour fire rating, as well as all of the vertical wood structural panel shear wall segments as well. And then on the right-hand side, we see for Galt Place, they enclosed the joists and the panels, but they left the glulams exposed. And the reason why the architect shared was that they felt, one, these glulams were too pretty to wrap them and enclose them. They wanted to leave them visible as a design feature for their appearance. And then secondly, if there was ever a leak or moisture in contact with these beams in the future, it would be much easier to monitor, detect, and repair as opposed to if it was enclosed and not visible. Because the glulams were left exposed, they still had to meet the 1-hour fire resistance rating. And so there are multiple ways to do so through the building code. One way to do so is to calculate your fire resistance using our tech note Y245. And what you see on our left-hand side, this figure shows you a typical impact of the design where you're going to have an additional tension lamination, at least on the bottom, if not top and bottom, knowing that when the glulam is exposed to fire, it will char, and then the charring protects the remaining core of that beam. So you have compromised some of the strength of where we put our best wood in our glulam, so by having that additional tension lam, you still have the strength where you need it, and now you have this protective layer provided around it. On the right-hand side, we see a fire test that was applied same fire test to a glulam and a steel beam, and again, just this charring capability and how wood can perform so well. Another design challenge was communication, and both teams emphasized how important it was to communicate early and often among all their subconsultants. And Oceana at Warner Center used a BIM model, Building Information Modeling. As shown on the right-hand side, we see the BIM model and then the same section under construction, and they felt that this helped them head off a multitude of what would have been framing mistakes in advance. They also did multiple schematic designs with this tool so that they were able to identify the most effective, efficient podium design, as this was new for these project teams. They were both familiar with this podium construction, but wood podium specifically was something new. And with the discussion on the glulams being so unique in size, both projects also worked with the glulam manufacturer during the design phase to make sure they were designing a glulam that would be efficient, cost-effective, and available. So certainly you want to do that research in advance as well. And working with the hanger manufacturer to do the testing and providing that design for those steel hangers was done as well. So lots of things to consider as far as communication goes. For field modifications, I mentioned earlier today that for Galt Place, this engineer allowed them to cut larger holes up to 5 inches in size, but that had to be coordinated and certainly wasn't just a general note on the plans, but they felt that this was useful and in a way to be able to create a more efficient system. Whereas Oceana at Warner Center did not allow as much hole cutting in the field, and they did have more chases and runs as a result, but still felt that it was a superior system. And then this diagram is simply from our glulam cutting and notching, which shows the zones that would be best for where you would want to allow hole cutting to occur. The topic of shrinkage was not mentioned by either design team as being a challenge, yet providing this presentation nationwide, we've had this question come up enough that we've added some slides to address shrinkage. And so according to the building code, if the structure has 2 floors and a roof, then you don't need to address shrinkage. So it's for buildings that are more than 2 floors and a roof. Therefore, Galt Place didn't even need to address shrinkage, whereas Oceana did. And as I said before, they are very familiar with this type of construction, so they didn't feel that it was a concern for them. But if you're looking at wood shrinkage, some things to keep in mind, and this is a nice graphic that shows how wood shrinks as opposed to, say, a sugar cube. So where we see a sugar cube would shrink the same in each direction. With wood, it shrinks very little parallel to the grain of the wood, and the shrinkage occurs perpendicular to the grain. Therefore, the zone of movement is primarily in the horizontal, the floor framing section here. So our plates, our rim board, this is where we're going to have to calculate the most shrinkage or account for it. So rules of thumb to keep in mind is that, again, wood primarily shrinks perpendicular to grain. You can neglect the parallel to grain shrinkage. The amount of shrinkage is going to be directly proportional to the change in moisture content, as we talked about before. What is the moisture content at the end of manufacturing as opposed to once it arrives at the job site? The higher the moisture content at the time of construction, then the more shrinkage that can occur in the structure itself. So some tips. For every 4% change of moisture content, you can assume about a 1% dimensional change. Prefabricating these materials is useful, and that's one thing that Oceana at Warner Center did. The framer prefabricated a lot of the wall sections, the floor materials out in the desert, then they shipped it out to the job site. So they eliminated the shrinkage during their prefabrication portion. The use of joist hangers, so you can minimize that zone of movement if you're hanging your floor off of your wall as opposed to having it platform framed. Loading your floors as soon as possible is useful. Often stacking the drywall within the units is done to, again, get that load onto the floors. And then to remember that you do need to accommodate movement for plumbing and electrical. And limiting dissimilar materials. For more information, you can check out this tech note on the Western Wood Products Association website. And finally, we're to the benefits of these structures. If there weren't benefits, there wouldn't be any need to be discussing these case studies. Yet, they did find that there was a enhanced constructability. There were fewer trades on the job, and as a result, less mobilization time to build the structure from top to bottom. They were able to have more trades working in that podium level at the same time because they weren't waiting for the concrete to cure. And the framing efficiency was found earlier because, again, we had the same framing group working from the podium and up. And they felt, for Galt Place in particular, that there was a large pool of experienced and competitive labor to choose from, which brought the cost down for construction. And it was easier to provide field modifications at the podium level for a wood podium as opposed to concrete. Structurally speaking, the wood podium was much less massive, and when it comes to lateral design, that is a major factor in the design loads. So as mentioned before, they were able to utilize wood structural panel shear walls at that first level, whereas that would not be possible with a concrete podium. They also were able to design smaller foundations as a result. They focused on continuity, and so if they can minimize penalties that would be required. And there were fewer design team members from a structural aspect. Often with a traditional podium, you may have one design team doing the concrete podium and another design team doing the wood superstructure. So in both of these projects, it was a single engineering firm and team for top to bottom. Sustainably speaking, we've touched on this in concept already, that wood is a sustainable building material to begin with, and the Oceano project further pursued a LEED for Homes multifamily silver rating. And Galt Place, although they did not specifically pursue any green rating system, did note that the use of wood met the requirements of the building program for the development of that city, Galt, where they wanted to minimize the use of natural resources that they were impacting. So lastly, the projects were more economical. And again, if they weren't more economical, again, it wouldn't matter about all the other benefits. It would likely be a non-issue. So Oceano estimated that even though this was the first time they were doing wood podium, that it was 2/3 the cost of a concrete podium. Galt Place received only a single change order, and it was a $2 million credit that the architect accounts was due primarily to the use of wood. If you'd like to read more details about this, you can download the white paper from the SEOC convention proceedings at this link. We also have our APA case study, which is a shorter, glossier version of the SEOC white paper, and that's available on our website as well, Form N110. It's also available on our website, apawood.org, as well as the woodworks.org website. The Engineered Wood Construction Guide that I've mentioned multiple times thus far is a cover shot is shown here. It's Form E30, so you can search for it on our website under the publications in either way. And then our Designer Circle, if you were a former member of our Professional Associates program, you would have been grandfathered into our Designer Circle, and this was just a updated version of the Professional Associates Program, a way to keep those who are interested in new publications that are available, new updates from APA, different training events that are coming up. So again, it's shown here with our new website specific to the Designer Circle. We've reorganized a lot of our content online here as well to make it easier to find. We have a login. The reason why we ask you to log in is just, again, this is very useful to us as an association to know which publications are being downloaded, because that shows us what we need to focus on as far as keeping up to date and working on moving forward. And that concludes the webinar content. I'm glad to answer any questions and comments at this time. My contact information is shown here, and look forward to assisting you today or later down the road when you have any further engineered wood product questions.